Very good morning, students. Today we will see about the p block elements. Yesterday the slide was not clear. That's what today we are seeing that another slide where it will be clear with you. Let us start with the periodic table. You are knowing on the left side of the periodic table there are alkali metals, alkaline earth metals. In between or in middle part of the periodic table there are the transition metals, and right side of the periodic table there are the p block elements and the noble gas, and below of the periodic table there is the a block elements. So the S, P, D, F, these are the atomic orbitals, and these atomic orbitals, when that elements, any element in its outermost orbital, if that electron it is to be entered in it, so that elemental series which is to be named by that block element. Now today we will see about the p block elements. It means that elements in outermost shell, it is the p orbital, and that electrons are entered in that p block elements. So p orbital, it is of having three types: px, py, pz, according to the universal axis x, y, z. Each one has that a positive and negative lobes of that electron, and that's what each px it has the 2 electron capacity, y it is of having 2 electron capacity, and the z it is of 2. So whole of p block or the p orbital, it is having that the capacity to contain the 6 electrons. So out of 1 to 6, when that electrons are entered in a p orbital, likewise that families are made. Let us see one by one. That is the boron family, carbon family, nitrogen family, oxygen family, halogens, and the noble gases. Noble gases are NS2 and P6. So all the orbitals are clearly filled, and that's what, that they are inert, or we can say they are neutral in action. So this is about the noble gas element and the p block elements. So on the slide you have seen about that the periodic table where that the p block elements are entering. Main group of elements, they are include alkali metals, it means group 1, alkaline earth metals in the periodic table, group 2, which is on a left side, boron family, that is group 13, carbon family, that is group 14, nitrogen family, that is group 15, oxygen family, group 16, halogen family, group 17, and the noble gases, group 18. All groups, that is means vertical columns found in the periodic table, are called families. All elements in each group or family share many physical and chemical properties equally, or we can say same, and that's what they are filled in a one of family or one of group. One trend in the periodic table is that elements of the same family share properties. Let us see the first, that is the group 13 of p block element, that is the boron family, or group number 13 elemental series. Let us one by one. So their electronic configuration, it is that NS2 NP1, and that's what the elements which are to be sharing here, they are 2, 3, 4, 5. They are having that the groups which are showing that 2s2 2p1, 3s2 3p1, 4s2 4p1, 5s2 5p1, 6s2 6p1. The elements, they are shared in a boron family. So this is the group 13, NS2 NP1 electronic configuration, +1 and the +3 oxidation state they can show, and they are reactive as the one unpaired electron is there. And the elements which are to be sharing here, they are boron, aluminium, gallium, indium, and the thallium. Boron, it is having outermost electronic configuration 2s2 2p1, aluminium 3s2 3p1, gallium 4s2 4p1, indium 5s2 5p1, and the thallium, that is 6s2 6p1. Boron is fairly rare element. The abundance of the boron in the earth crust is less than 0.0001% by mass. Aluminum is the most abundant metal and the third most abundant element in the earth crust, which is 8.3% by mass. After oxygen, which is of 45.5 mass, and the silicon, it is the 27.7%. Let us see the properties of these elements. The general properties of these elements, the electronic configuration, the outermost electronic configuration as we have seen on the slide, that is N:2np1. Boron and aluminum have noble gas core. Gallium and indium have noble gas plus 10d electrons, and thallium has the noble gas plus 14f electrons plus 10d electron cores. Thus, the electronic structure of these elements are more complex than for the first two group of elements. So, as the electrons and the orbitals, or we can say shells, they are increasing by the atomic number downwards the group. So, the structure and the behavior, it will varies. Atomic and the ionic size. Size, it is means that how many electrons and the orbitals are around the nucleus of each element. On moving down the group, for each successive member, one extra shell of electron is added, and therefore atomic radius is expected to increase. As the shell is increased, so naturally the size also increase. However, a deviation can be seen. Atomic radius of gallium is less than that of aluminum. The presence of additional 10d electrons offer only poor screening effect. And for the outer electrons from the increased nuclear charge in gallium. Consequently, the atomic radius of gallium 135 pm is less than that of the aluminum, which is 143 pm. This is one of the reasons that it is showing up poor screening effect. Ionization enthalpy. The ionization enthalpy values is as expected from the general trends do not decrease smoothly down the group. The decrease from boron to aluminum is associated with increase in size. The observed discontinuity in the ionization enthalpy values between aluminum and the gallium and between indium and the thallium are due to the inability of d and f electrons, which have low screening effect, to compensate the increase in nuclear charge. The order of ionization enthalpies as expected is delta H1, which is less than delta H2, which is less than delta H3. Next property, it is the electronegativity. Down the group boron to thallium, as you have seen, or we can see clearly that the values are somewhat lower, still indium and thallium it little bit increased. Electronegativity first decreases from boron to aluminum and then increases marginally. This is because only the discrepancies in atomic size of the element. Boron is non-metallic in nature. It is extremely hard and black color solid. It exists in many allotropic forms. Boron has unusually high melting point. Rest of the members are soft metals with low melting point and high electrical conductivity. Gallium with unusual low melting point, that is 303 Kelvin, could exist in liquid state during summer. Its high boiling point 2676 Kelvin makes it is useful material for measuring high temperatures, and density of the elements increases down the group from boron to thallium. Let us see one by one the chemical properties of this family, the oxidation state and trends in chemical reactivity. Boron doesn't have +3 oxidation state. It forms only covalent compounds. Aluminum is a highly electropositive metal. It loses electrons and forms +3 oxidation state. Gallium, indium and thallium both +1 and +3 oxidation states are observed. The relative stability of +1 oxidation state progressively increases for heavier elements. Thus, aluminum, which is less than gallium, which is less than indium, which is less than thallium. The compounds in +1 oxidation state are more ionic than those of the +3 oxidation state. Due to what? That the 2 electrons which are present in a NS2 or orbital. In trivalent state, the number of electrons around the central atom in a molecule of the compounds of these elements, boron in BF3, will be only 6. Such electron deficient molecules have tendency to accept a pair of electrons to achieve stable electronic configuration, and thus they behave as Lewis acids. The tendency to behave as Lewis acid decreases with the increase in size. Thus, down the group boron to thallium, as the size is increased, the tendency to behave as a Lewis acid, it is decreased. BCl3, that boron trichloride, easily accepts a lone pair of electrons from ammonia to form BCl3 NH3. BF3, which is Lewis acid, Lewis base NH3, there is the formation of acid base adduct, which is F3B NH3. LCl3 achieves stability by forming a dimer, which is shown on the slide. So this is about LCl3, which it shows that the structure, it is aluminium to aluminium, they are to be terminal 4 chlorine, and in middle they are 2 chlorine which is there. So this dimer which is formed by the aluminium trichloride. Reactivity towards the air of these elements, boron is unreactive in crystalline form. Aluminium forms a very thin oxide layer on the surface which protects the metal from further attack. Amorphous boron and aluminium metal on heating in air, boron B2O3 and aluminium dialuminum trioxide respectively with dinitrogen at high temperature, they form nitrides. Likewise, the reaction which is given to E plus 3O2, there is the 2E2O3, and to E plus N2 there is the 2En. The nature of this oxide varies down the group. Boron trioxide is acidic and reacts with the basic metallic oxides forming metal borates. Aluminium and the gallium oxides are amphoteric, and those of indium and the thallium are basic in nature. Thus, these are reactive towards the air. Somewhat the reactivity towards acids and alkalis. Boron does not react with acid and alkalis even at moderate temperature. Aluminum dissolves in mineral acids and aqueous alkalis and thus shows amphoteric character. Aluminum dissolves in dilute HCl and liberate dihydrogen. The reaction which is also showing to aluminum plus 6 HCl, there is the formation of 2Al3 which is in aqueous state plus 6Cl in aqueous state and 3H2 which is in a gaseous state. Concentrated nitric acid renders aluminum passive by forming a protective layer, oxide layer on the surface. Aluminum also reacts with aqueous alkali and liberates dihydrogen. To aluminum plus 2NaOH plus 6H2O, there is the formation of 2Na plus AlOH4 aqueous plus 3H2, sodium tetrahydroxoaluminate which forms. Reactivity towards the halogen. These elements react with the halogen to form trihalides. So 2E plus 3X2, there is the formation of 2EX3. Likewise, fluorine, chlorine, bromine, iodine, trihalides which is to be formed by these elements. Important trends and the anomalous properties of boron. The trichlorides, bromides and iodates of all these elements being covalent in nature are hydrolyzed in water. Species like tetrahedral MOH4- and octahedral MOH2O6 plus except in boron exist in aqueous medium. The monomeric trihalides being electron deficient are strong Lewis acid. Boron trifluoride easily reacts with Lewis bases such as NHG to complete octet around the boron. F3B plus NH3 with lone pair, there is the formation of F3B NH3. Due to the absence of d orbitals, the maximum covalency of boron is 4. Most of the other metal halides are dimerized through the halogen regime. The metal species completes its octet by accepting electrons from halogen in this halogen-rich molecule. Some important compounds of boron, that is borax. Everyone knows it is most important compound. It is white crystalline solid. Formula Na2B4O7 10H2O. Borax dissolved in water to give alkaline solution, and it is the orthoboric acid. On heating, borax first loses water molecule and swells up. On further heating, it turns into transparent liquid which solidifies into the glass-like material known as a borax bead. So, boric anhydride, when it heated, there is the formation of sodium metaborate. Borax bead test is used to identify transition metals in the lab as they give characteristic color when ignited with the borax. Example, cobalt oxide gives blue color with bead. Second compound of the borax, it is the orthoboric acid. It is white crystalline solid with soapy touch. It is sparingly soluble in water but highly soluble in hot water. It is prepared by acidifying an aqueous solution of the borax. So the borax plus 2HCl plus 5H2, there is the formation of a NaCl 4BOH thrice. The structure of the boric acid, which is shown on the slide, it has a layer structure in which planar BO3 units are joined by hydrogen bond, which is very clearly shown. Boric acid is weak monobasic acid. It is not a protonic acid but acts as a Lewis acid by accepting electrons from hydroxyl ion. On heating, orthoboric acid above 370 degree Kelvin forms metaboric acid HbO2, which on further heating yields about boric oxide B2O3. Third compound, it is the diboron. It is prepared by treating boron trifluoride with lithium aluminum hydride in diethyl ether. There is the formation of a 2B2H6, that is the diboron. Lab preparation, that is the oxidation of sodium borohydride with iodine. There is the formation of a diboron. And industrial preparation, diboron is produced on industrial scale by the reaction of BF3 with sodium hydride and 450 degree Kelvin temperature. There is the formation of a diboron. Properties, it is a colorless gas, highly toxic, boiling point 180 degree Kelvin, catches fire spontaneously upon exposure to air. It burns in oxygen, releasing an enormous amount of the energy. So it is highly flammable. B2H6 plus 3O2, B2O3 plus 3H2O. Delta it is 1976 kJ per mole, and boranes are readily hydrolyzed by water to give boric acid. The reaction which is to be shown here, B2H6 plus 6H2O, there is the formation of 2BOH thrice in aqueous and 6H2 gas which liberates. Diboron undergoes cleavage reaction with Lewis bases to give boron adders BH3L. B2H6 plus 2NMe3, there is the formation of 2BH3 and Me3. Reaction of ammonia which is shown on the slide, see it clearly. Structure of diboron, it is like that. The dimer terminal hydrogens are there and bridging by the hydrogen. The 4 terminal hydrogen atoms and the 2 boron atoms lie in one plane. Above and below this plane there are the 2 bridging hydrogen atoms. The 4 terminal BH bonds are regular to center 2 electron bonds, and 2 bridges BHB bonds are 3 center 2 electron bonds, that is banana bonds. Boron also forms a series of hydridoborates. The most important one is the tetrahedral BH4 minus ion. Both LiBH4 and the NaBH4 are used as reducing agent in organic synthesis. Use of boron and its compound. Boron fibers are used in making bulletproof vest and light composite material for aircraft. Boron 10 isotope has high ability to absorb neutrons, and therefore metal borides are used in a nuclear industry as protective shields and control rods. The main industrial application of borax and boric acid is the manufacture of heat-resistant glasses, that is pyrex, and glass wool and the fiberglasses. Borax is also used as a flux for soldering metals and as consistent of medicinal soaps. An aqueous solution of orthoboric acid is generally used as a mild antiseptic. Use of aluminum and its compound. Aluminum is used extensively in industry and everyday life. It forms alloys with copper, manganese, magnesium, silicon and zinc. Aluminum and its alloys can be given shapes of pipe, tubes, rods, wires, plates, foils and therefore find uses in packaging, utensils making, constructions, aeroplanes and the transportation industries. Group 14, that is the carbon family. Carbon family consists carbon, silicon, germanium, tin and lead, these elements. Carbon is the 17th most abundant element by mass in the earth crust. The elemental state it is available as coal, graphite, diamond. Silicon is the second 27.7 by mass most abundant element on the earth crust. Germanium exists only in traces. Tin occurs mainly in cassiterite SN.II and lead as a galena PbS. General properties, that is the electronic configuration of these elements, that is Ns to Np2. The inner core of the electronic configuration of element in this group also differs. Covalent radius, there is the considerable increase in covalent radius from carbon to the silicon. Thereafter, from silicon to lead, a small increase of radius which is observed, and this is due to the presence of completely filled d and f orbitals in heavier members. Ionization enthalpy. In general, the ionization enthalpy decreases down the group. Small decrease in ionization of enthalpy from silicon to the germanium to tin and slight increase in tin to lead is the consequences of poor shielding effect of intervening d and f orbitals and increase in size of the atom. Electronegativity. Due to small size, the elements of this group are slightly more electronegative than group 13 elements. The electronegativity values for elements from silicon to lead are almost same. Physical properties. All group 14 members are solid. Carbon and silicon are non-metal. Germanium is metalloid, whereas tin and lead are soft metals with low melting points. Melting points and boiling points of group 14 elements are much higher than those of the corresponding elements of group 13. Chemical properties. The oxidation state as Ns to Np2 general electronic configuration. So the general oxidation state of these elements, it is +2 and the +4. In heavier members, the tendency to show +2 oxidation state increases in the sequence germanium, which is less than tin, which is less than lead. It is due to the inability of Ns2 electrons of valence shell to participate in bonding, that is inert pair effect. Reactivity towards the oxygen. All members forms oxides, mainly two types of oxide, monoxide and dioxide, that is MO and MO2. Oxides in higher oxidation state of elements are generally more acidic than those of lower oxidation state. The dioxide CO2, SiO2, GO2 are acidic, whereas SNO2 and lead-O2 are amphoteric in nature. Among monoxide, carbon monoxide is neutral. Germanium oxide is distinctly acidic, whereas tin oxide and lead oxide are amphoteric. They form hydroxides and carbon, silicon, germanium, which are not reacted with the water. Tin decomposes steam to form dioxide and dihydrogen gas with the water, and lead is unaffected by the water, probably because of a protective oxide film in formation. Halogen reactivity, these elements can form halides, which is MX2 and MX4. Most of MX4 are covalent in nature. Exceptions are tin tetrafluoride and lead tetrafluoride, which are ionic in nature. Stability of dihalide increases down the group. Except CCl4, other tetrachlorides are easily hydrolyzed by water because of the central atom can accommodate the lone pair of electrons from oxygen atom of water molecule in d orbital. Example, silicon tetrachloride undergoes hydrolysis by initially accepting lone pair of electrons from water molecule in d orbitals of silicon, finally leading to the formation of SiOH4 as shown below. So there is the salicylic acid which is formed. Important trends and the anomalous behavior of the carbon. Let us see one by one. Maximum covalence is 4 because it is on the s and p orbitals. Others have d orbitals, hence can expand their covalency. Carbon also has unique stability to form p-pi multiple bonds with itself and with other atoms of small size and high electronegativity. Examples of multiple bonding: C double bond C, C triple bond C, C double bond O, C double bond S and C triple bond N. Maximum catenation because of strong CC bond. Allotropes of carbon. Carbon exhibits many allotropic forms, both crystalline as well as amorphous. Diamond and graphite are two well-known crystalline forms of carbon. In 1985, third form of the carbon known as fullerene, which was discovered, and it is highly elaborated. Diamond has crystalline lattice structure. In diamond, each carbon atom undergoes sp3 hybridization and linked to 4 other carbon atoms using hybridized orbitals in the tetrahedral fashion. The carbon-carbon bond length is 154 picometer, that is pm. The structure extends in shape and produces a rigid three-dimensional network of carbon, which is shown. It is very difficult to break extended covalent bonding, and therefore diamond is the hardest substance on the earth. Uses of diamond: it is used as an abrasive for sharpening hard tools, in making dyes, in the manufacture of tungsten filaments for the electric light bulbs, and in jewelry. Third, it is the graphite. It has layered structure, which is shown in the diagram. Layers are held by van der Waals forces, and distance between two layers it is 340 pm. Each layer is composed of planar hexagonal rings of the carbon atoms. Carbon-carbon bond length within the layer it is 141.5 pm. Each carbon atom is hexagonal ring, undergoes sp2 hybridization and makes 3 sigma bonds with 3 neighboring carbon atoms. 4 electrons forms a pi bond. The electrons are delocalized over the whole sheet. Electrons are mobile, and therefore graphite conduct electricity along the sheet. Graphite cleaves easily between the layers, and therefore it is very soft and slippery. For this reason, graphite is used as a dry lubricant in machines running at high temperature. Third allotrope of carbon, it is fullerenes. It's made by the heating of graphite in an electric arc in the presence of inert gases such as helium or argon. Fullerenes are the only pure form of carbon because they have smooth structure without having dangling bonds. Fullerenes are cage-like molecule. As like a holy ball, C60 molecule has a shape like saucer ball or called Buckminster fullerenes. It contains 26 membered rings and 12 5-membered rings. Each carbon atom forms 3 sigma bonds with other 3 carbon atoms. The remaining electrons at each carbon is delocalized in molecular orbitals, which in turn give aromatic characters to molecule. A 6-membered ring is fused with the 6 or 5-membered rings, but a 5-membered ring can only fuse with 6-membered rings. All the carbon atoms are equal and they undergo sp2 hybridization. This ball-shaped molecule has 60 vertices, and each one is occupied by one carbon atom, and it also contains both single and double bonds with CC distance 143.5 pm and 138.3 pm respectively. Other forms of elemental carbon like carbon black, coke, charcoal are all impure forms of the graphite or fullerenes. Use of carbon. Graphite is used for the electrodes in batteries and industrial electrolysis. Being highly porous, activated charcoal is used as adsorbing poisonous gases. Carbon black is used as black pigment in black ink and as filler in automobile tires. Coke is used as a fuel and largely as reducing agent in metallurgy. Diamond is a precious stone and used in jewelry. Some important compounds of carbon and silicon. Oxides of carbon. Two important oxides of carbon are carbon monoxide and the carbon dioxide. Carbon monoxide is formed direct oxidation of carbon in limited supply of oxygen. 2 carbon plus oxygen, yet there is the 2 carbon monoxide forms. On small scale, pure carbon monoxide is prepared by dehydration of formic acid HCOH plus concentrated H2SO4 at 373 Kelvin. There is the formation of water and the carbon monoxide. On commercial scale, it is prepared by passing of steam over hot coke. The mixture of carbon monoxide and water thus produced is known as water gas or synthesis gas. Carbon plus water 473 minus 1273 Kelvin. Carbon monoxide gas plus H2 gas. When air is used instead of steam, a mixture of carbon monoxide and N2 produce, which is called producer gas. 2C plus O2 plus N2, 1 to 73 Kelvin temperature, 2 CO, that is in a gaseous state, and 4 nitrogen gases. Properties. Now the properties: carbon monoxide is colorless, odorless and almost water insoluble gas. It is powerful reducing agent. This property of carbon monoxide is used in the extraction of many metals. In carbon monoxide molecule, there are 1 sigma and 2 pi bonds between carbon and the oxygen, that C triple bond O. Because of the presence of the lone pair on carbon, CO molecule acts as a donor and reacts with the certain metals when heated to form metal carbonyls. The highly poisonous nature of carbon monoxide arises because of its ability to form complex with the hemoglobin, which is about 300 times more stable than the oxygen hemoglobin complex. This prevents hemoglobin in the red blood corpuscles from carrying oxygen around the body and ultimately resulting in a death. Another oxide of a carbon, that is the carbon dioxide, which is prepared by complete combustion of carbon and the carbon containing fuels in excess of air. So carbon plus O2, there is the formation of CO2. In the laboratory, it is conveniently prepared by the action of dilute HCl on calcium carbonate, and on commercial scale it is obtained by heating limestone. The properties of carbon dioxide are: it is colorless and odorless gas. With water it forms carbonic acid, which is diabasic and weak acid. Carbon dioxide can be obtained as a solid in the form of dry ice by allowing the liquefied CO2 to expand rapidly. And uses of carbon dioxide: it is dry ice is used as a refrigerant for ice cream and the frozen food. Gaseous carbon dioxide is extensively used to carbonate soft drinks. Being heavy and non-supporter of combustion, it is used as fire extinguisher. A substantial amount of carbon dioxide is used to manufacture of urea. In carbon dioxide molecule, carbon atom undergoes sp hybridization. Two sp hybrid orbitals of carbon atom overlap with two p orbitals of oxygen atoms to make 2 sigma bonds, while other 2 electrons of carbon atom are involved in p-pi bonding with oxygen atom. This results in this linear shape with both carbon and oxygen bonds with equal length 115 pm with no dipole moment. The resonance structure are which are shown on the diagram. Silicon dioxide. Silicon dioxide, commonly known as silica, occurs in several crystallographic forms. Quartz, cristobalite and tridiamide are some of the crystalline forms of silica, and they are interconvertible at suitable temperature. Silicon dioxide is covalent three-dimensional network solid in which each silicon atom is covalently bonded in a tetrahedral manner to 4 oxygen atom. Each oxygen atom in turn covalently bonded to another silicon atom as shown in a diagram. Silica in its normal form is almost non-reactive because of very high silicon-oxygen bond enthalpy. The quartz is extensively used as a piezoelectric material. It is made possible to develop extremely accurate clock, modern radio and television broadcasting and mobile radio communication. Silica gel is used as a drying agent and as a support for chromatographic materials and catalyst. Silver, an amorphous form of silica, is used in filtration plants. Silicones. They are a group of organosilicon polymer which have R2SiO, the bond, as a repeating unit. The starting material for the manufacture of silicones are alkyl or the aryl substituted silicon chlorides. Hydrolysis of dimethyl chlorosilane followed by the condensation of polymerization yields slightly chain. This is the reaction which is of showing that how they are the silicones which are to be made. Silicones being surrounded by non-polar alkyl groups are water repelling in nature. They have in general high thermal stability, high dielectric strength and resistance to oxidation and the chemical. They are used as a sealant, grease, electric insulator and for waterproofing of fabrics. Being biocompatible, they are also used in surgical and cosmetic plants. Next, silicates. A large number of silicates minerals exist in nature. Some of the examples are feldspar, zeolites, mica, asbestos. The basic structural unit of silicates is SiO4, in which silicon atom is bonded to 4 oxygen atom in tetrahedron fashion. In silicates, either the discrete unit is present or a number of such units are joined together via corners by sharing 1, 2, 3 and 4 oxygen atom per silicate units. The negative charge on the silicate structure is neutralized by positively charged metal ions. If all the 4 corners are shared with other tetrahedral units, 3-dimensional network is formed. 2 important man-made silicates are glass and cement. Zeolites. If aluminum atoms replace few silicon atoms in 3-dimensional network of silicon dioxide, overall structure known as aluminosilicate acquires a negative charge. Cations such as sodium plus, potassium plus, calcium 2 plus balance the negative charge. Examples feldspar and the zeolite. The structure which is shown on the slide. Zeolites are widely used as a catalyst in petrochemical industries for cracking of hydrocarbons and isomerization. A type of zeolite is used to convert alcohols directly into gasoline. Hydrated zeolites are used as ion exchangers in softening of hard water. This is about the group 14 elements. Stay home. This is the online lecture of P block elements. Thank you very much. If you have any difficulty, please mail me. Thank you. Thank you very much.